Chris Leininger from Rice University. We're going to talk about 3-manifolds and Veech groups.
Thanks. This has been really great. I really appreciate everything. And as a last speaker, maybe we can all thank Verberne and Ernesto for putting this all together. Okay, so yeah, I think this is pretty kind of relaxed last talk. I'm going to tell you about one of my favorite conjectures that I am sadly not going to tell you the solution to, but maybe if you haven't seen this before, you'll be interested and somebody can figure it out. Let me start. S is going to be a closed surface of genus G at least 2. Most of what I am going to say is true for any finite type surface. I'm going to talk a little bit about some infinite type surfaces at the end of the talk. That say they sort of very naturally come up in this in the discussion that I'm going to explain. So I'm going to equip this surface with some extra structure, so I'm going to give it a complex structure and a holomorphic quadratic differential. Okay, so now I want to think about this geometrically as sometimes called a half translation structure, which is a really stupid name. So half translations. Oh, maybe somebody made that name up. I'm sorry. So translation structures are something that people are maybe more familiar with. They come from a holomorphic abelian differential, and they give you an atlas of charts where the transition functions are translations, and here the transition functions are half translations, which means translations and possibly rotations through 180 degrees. So let me, if you haven't thought about this before, I'll give you some examples to kind of think about as we go. So here you should think about building this surface out of, these are supposed to all be squares. I don't know if you can read that in the back. It's not so important what the actual identifications are, but they're identifications. So this top edge is glued to this top edge by a rotation through 180 degrees, about some point here in the middle. And then there are various other sides that are identified by translations. Okay, so these are all, let's say, unit squares. When I do this gluing, I get a flat metric on the surface, or if you like, I've got the differential dz squared on the Euclidean plane is invariant under translations and rotation through 180 degrees. So that dz squared descends to a holomorphic quadratic differential on the surface. And this surface happens to be a surface of genus 4. So I colored these in so you could sort of see where things get identified. So all these blue bits get identified to a single point. That gives rise to some singularity in the Euclidean metric. This would be green. The green parts get identified. That gives you another singularity. And then the red ones get identified. That's another one. Everywhere else, there's this kind of horizontal and vertical foliations on the surface. So the surface is singular foliation with 3 singularities and 2 singular transverse foliations. Okay. And then the object that I'm interested in associated to this is the affine group. Okay, so here you think about, we've got this Euclidean cone metric, this flat metric, and I want to look at orientation preserving homomorphisms from the surface to itself, which are affine with respect to this structure. So if you think about this is given by an atlas of charts, where the transition functions are as I described earlier, then the derivative, there should be diffeomorphisms in that atlas of charts, and the derivatives should be constant. So they should be affine in this atlas. Okay. So that's kind of the object that I'm interested in, this affine group of one of these half translation structures. And I can think about this as a subgroup of the mapping class group. Another way to think about this, which is really useful for another perspective. So the complex structure in the holomorphic quadratic differential, they define a tychomolar disk. So a holomorphic isometric embedding of the hyperbolic plane with a Poincare metric into tychomolar space. And this affine group is really the stabilizer in the mapping class group of that tychomolar disk. So you can either think about it as as a stabilizer of a tychomolar disk or as these affine homomorphisms. All right, there's the picture again, and there's a derivative map because the derivative is constant in these local coordinates. I can compute the derivative. Notice that we're in PSL2 because the local coordinates are only defined up to translation and rotation through 180 degrees. So if I do a rotation through 180 degrees, the derivative, depending on which coordinate chart I choose, might change by plus or minus the identity. So the derivative is really only defined in PSL2R. And if you want to think instead about this isometrically embedded tychomolar disk, the derivative is really mapping into, since it's going into PSL2R, that's the isometry group of the hyperbolic plane. So this is just, when I act on that copy of the hyperbolic plane, these are the isometries that I see. So it's another way to think about what this affine group is. Okay. So just some examples, again, if you haven't thought about this before. So here's my surface again. Now I drew in some curves on the surface. So if you follow this black horizontal line over here, this gets identified up here, comes out over here, and comes back. So this two black lines together give me a simple closed curve on the surface. And these blue ones give me a simple closed curve, and the red one gives me another one. So I've got the horizontal squares here kind of line up to give me 3 cylinders on the surface, 3 Euclidean cylinders, with the core curves being the black curve, the red curve, and the blue curve. And then there's also 3 vertical cylinders. So there's the gray curves get identified to a single curve, so that gives me 1 cylinder. And then there's a green one, a yellow. Oh no, there's 4. Sorry, and then this one. There's 4 cylinders.
So there's only one non-top bottom identification. It's the 2.
There's only one non-top bottom. I'm not sure what that means.
Well, on the left square.
Yeah.
The leftmost square. The top of that square is identified to the bottom of it, right?
Oh, this 3 and this 3, you mean?
Yeah, that one.
Yeah.
Yeah. Okay.
Well, and then these this 8 gets identified down here. It's 9 over here. Okay, so oh, that didn't show up so well. Okay, well, I'm going to let TA be the Dane twist in A1, which is this black curve. TA2 is the Dane twist in this blue curve. I'm going to take the third power of that, and then TA3 is this red curve. I'm going to take its 6th power, and I'm going to take the product of those Dane twists. Why am I doing that? Because those Dane twists, this is just 1 square. The blue is giving me 2 squares, and the black's giving me 6 squares. So if I do those Dane twists, I can actually do them as affine Dane twists on each of those Euclidean cylinders. And when I do that, the derivatives agree on all of the cylinders. So I can compute the derivative of those horizontal Dane twists, and it's the matrix 1, 6, 0, 1. Right, and then likewise, maybe it's hard to see, but if I do these various powers, 6 powers of these little Dane twists and the 1 power of the big the big Dane twist, that's also affine, and its derivative is 1, 0, negative 6, 1.
And the genus is 4?
The genus is 4. I think. Possible, I think. Okay. Okay, so I'm going to write PSLXQ for the image of the derivative of the affine group. And this is what's often called the Veech group of the quadratic differential or the Teichmuller disk. Actually, I think maybe this is now what we're calling Veech groups these days. I think when I first started thinking about this, people only called it a Veech group if this group is a lattice. Okay, so if the PSLXQ is actually a lattice in PSL2R. In this case, it turns out that it is a lattice. That's not obvious from these generators, but because the surface is tiled by squares, it turns out that you can realize this as a branched cover of a sphere with 4 mark points, and then the Veech group is just the liftable elements of the mapping class group of the sphere with 4 mark points. Okay. All right, so we can take the derivative. This gives us a homomorphism from the affine group to this Veech group, and this sits inside of a short exact sequence. The kernel here is the automorphisms of the quadratic differential. Okay, so these are automorphisms of the Riemann surface that also preserve the quadratic differential. So just some facts. These are easy exercises. I learned some of these from Thurston's bulletin paper of Geometry and Dynamics of Diffeomorphisms of Surfaces. So he gives a very nice construction of these Veech groups, these flat metrics. Whenever you have two multi-curves that fill your surface, you can do a positive Dane twist in one, a positive Dane twist in the other, and there's always one of these quadratic differentials for which those 2 multi-twists are in the affine group. So there are lots of examples of big affine groups. It's very pretty discussion in this paper. I later found out that actually that was not Thurston's original argument. So Thurston originally just did it for Dane twist, which is much easier. And then Veech did it for multi-twists. And then when Thurston published the bulletin article, he included this sort of more general thing. So this is often called the Thurston-Veech construction. Anyway, what are these easy facts? One is that this is a discrete group. So if you think about like the image in the isometry group, this PSLXQ is supposed to be the image in the isometry group of this Teichmuller disk. Well, the mapping class group acts properly discontinuously on Teichmuller space. So the stabilizer of this Teichmuller disk has to be a discrete group. I think this is one of the things that really got me sort of interested in thinking about these is if I have an element of the affine group, the derivative tells you a lot about the element. So we saw those 2 multi-twists where their derivatives were parabolic matrices. And in general, if your derivative is a parabolic, then your element, at least up to a power, is a multi-twist. Okay? Your element has finite order, if and only if the derivative is elliptic or trivial. And then f is pseudo-Anosov if and only if the derivative is hyperbolic. And I think often, at least when I was first learning about this a long time ago, the definition of pseudo-Anosov seemed so mysterious. And then when I read Thurston's bulletin paper and saw this construction and this fact, it really kind of opened up, like, so I could understand what pseudo-Anosov homomorphisms are. So let me just say, like, this last bit, what is this? Why is this true? What does it mean for the derivative to be hyperbolic? It means you have 2 distinct real eigenvalues, right? Well, those 2 distinct real eigenvalues give me 2 eigenspaces in each of the tangent space. And those eigenspaces, I can parallel translate them around. They're invariant because the derivative preserves those eigenlines. And that gives me 2 foliations on the surface. And what's happening to the leaves of those foliations? Well, one of the leaves in one direction are being stretched by one of the eigenvalues and the other being contracted by the other one. So it's a really sort of, I think, concrete way of thinking about what pseudo-Anosov homeomorphisms are. They're just these affine homomorphisms of these flat surfaces where you're stretching and contracting. Okay, so here's the definition. We're going to say that this structure xq is lonely if PSL-XQ is an elementary hyperbolic group. So if it's a cyclic, virtually cyclic group generated by a hyperbolic element. Sometimes people call that hyperbolic element, which we know is a pseudo-Anosov, sometimes they'll call that pseudo-Anosov lonely. I want to use this terminology for reasons that will become clear at the end of the talk. But this is the thing I'm interested in, our lonely XQ. And here's the conjecture that I mentioned earlier. I attribute it here to Verberne, Maser, Schmidt, and Zorch. This was in one of their problem lists from, I don't know, 15, 20 years ago or something. I don't know if they came up with this problem, but this is the first place I've seen it written down. And it says that if this Veech group contains a hyperbolic element, then generically at least, this XQ is lonely. Okay, what's another way to say that? Basically, if you take a generic pseudo-Anosov homeomorphism, it's in some Veech group, so maybe it's in some Veech group, which I'll say in a second, and the conjecture is that generically for a pseudo-Anosov, it virtually generates the Veech group, or it virtually generates the affine group. Okay, so there's not a single example. So whatever, okay, you might say, what does it mean to be generic? Well, who knows? But there's not a single example of a lonely XQ. How can that be? Kind of depressing state of affairs. So really, I would be happy just to see a single example. And I think if you could find a single pseudo-Anosov that virtually generated its affine group, that would probably be of interest to lots of people. Okay. So as I sort of suggested, every pseudo-Anosov homomorphism is actually in some affine group, and in fact, there's a essentially unique flat structure, so unique up to affine deformation. There's a unique affine structure for which F is in its affine group. So every pseudo-Anosov is in one of these, and you can just pick your favorite pseudo-Anosov and ask, is its quadratic differential lonely? Nobody knows a single example. And then maybe a little word of caution why this might be slightly difficult. In genus 2, if you look at quadratic differentials that are squares of holomorphic 1 forms, then there's no XQs that are lonely. Okay, so this is a theorem of Kalta and McMullen that basically says in genus 2, with a holomorphic 1 form, once you have one pseudo-Anosov, you have a bunch of them. In fact, you also have lots of parabolics. In fact, if you think about this as the PSL-XQ as a Fuchsian group, its limit set is the entire circle. So there's not only is there something else in the Veech group, there's lots of something else's in the Veech group. Okay, so if you want to try to do some kind of generic construction or say something about finding these lonely, sometimes the conjecture is called the lonely dude conjecture. Maybe not many people call it that. Maybe I call it that. So if you want to find generic set of pseudo-Anosovs and prove that they're lonely, where are you going to look? So one thing you could do is you could look inside of moduli space and look at closed geodesics, and then look at maybe a random closed geodesic. And I think a lot of people have thought really hard about that, but it seems hard to understand the Veech groups and to figure out. I mean, people know things about the orbit closures of the generic disk. But still, it seems really hard to understand from that perspective. So I want to describe another way of generating pseudo-Anosov homomorphisms that maybe this is kind of an advertisement that somebody can take this and actually figure out how to make it work. So let me explain how to generate lots of pseudo-Anosov homomorphisms. So I'm going to start with one pseudo-Anosov homomorphism. I'm going to construct a mapping torus. Okay, so R mentioned the mapping torus of a pseudo-Anosov the other day. So this is, I'm going to take the surface across the interval, and then I'm going to glue the top to the bottom by F. You could also glue the bottom to the top, but that would be wrong. So you should glue the top to the bottom. And what you get is a hyperbolic manifold. So that's great. But actually, the hyperbolic geometry of this manifold isn't so important for us. Instead, what I want to think about is the suspension flow on this 3-manifold. So the suspension flow, if you think about just coordinates on the surface, x, and then t coordinate in the interval direction, it's just the flow generated by the vector field d by dt. So it's just translation upward. So when you glue the bottom to the top, this local flow in the product turns into a globally defined global flow. And this is a 3-manifold that fibers over the circle. With fiber, the surface S. Oh, and Mustafa was using 0 for the genus here. This is just because I'm gonna talk about lots of other surfaces, so this is my seed pseudo-Anosov. Okay, so it's supposed to be it's supposed to fiber over the circle, and you can see it from this construction, right? If I take the product and I glue the top to the bottom by F, well, I can project the product onto the interval, and then the top of the interval gets glued to the bottom, and that's a circle. And so that projection onto the interval is your fibration over the circle. And the preimage of any point is a copy of the surface S0. And then the surface S is transverse to this flow, sort of by construction. And notice that if I flow for time 1, I start here at the bottom, and when I get to the top, because the top is glued to the bottom, the time 1 map of this flow sends the surface S0 to itself. So the first return map of this flow to the surface, well, what is it? If I start here and I flow up, and when I get to the top, I apply F. So the first return map is exactly the map F0. Okay, so that's the setup. I'm gonna think about these 3 manifolds, and I said this was a pseudo-Anosov flow, and I tried to draw a little picture here. So because the homeomorphism preserves these foliations, if I take the foliation and cross it with the interval, I get a 2-dimensional singular foliation on this product. But then because the foliation at the top is glued to the bottom, those foliations actually glue up to a singular 2-dimensional foliation on the 3-manifold. And they're invariant by the flow, just by construction. So that's really where the pseudo-Anosov flow description is. There's one foliation where when you flow, as you come back, you're sort of expanding, and then in the other direction, you're contracting. Okay, so now let's consider the situation where the first Betti number of this 3-manifold, this mapping torus, is at least 2. So this is the first Betti number of the 3-manifold is 1 more than the dimension of the fixed subspace in the axion homology. So if you think about the homomorphism F0 that we started with, just pick any one that has a fixed vector in homology. There are lots of examples. In fact, in this Thurston Bulletin article that I described, he gave a nice construction of pseudo-Anosovs in Torelli, where you fix lots of vectors. So you have big invariant homology, and then you have big first Betti number for the 3-manifold. Okay, and then I'm going to let alpha naught be its cohomology class, which is a Poincare dual of S0. You could think about 2-dimensional homology, but it turns out to be slightly better to think about cohomology here. Okay, so here's a picture. First cohomology is dimension at least 2. Alpha naught is some class in there, and then here's the kind of thing that gets us going. So there's this work that sort of started with work of Tischler, and then Thurston kind of built on that, and then Fried kind of built on that some more. So this what I'm going to describe here is kind of a combination of what I did. So there's a maximal open polyhedral cone, C, that contains alpha naught. So here's a picture. So C is where's it? There's supposed to be some colors here. So C is this cone here. It contains my class. There's also a linear function, which I'll get to in a second. But for every integral class in this cone, so I'm looking at the cone, and then I look at all the integer points in there. So for every integral class in there, you have the following nice property, that the Poincare dual, so that class is Poincare dual to a surface which is also transverse to this flow. And I'll draw a picture in a second to help describe what's going on. And the first return map is another pseudo-Anosov homomorphism. So how do I think about this? Here's a kind of a toy case where I'm going to go down. I'm in the way. Let me get out of the way. So think about the torus, and think about the flow. Just think about, so it's a square, and I'm going to do the flow, which is like d by dy. And here's a class, which is this curve, C naught, okay? So that's kind of like playing the role of my original surface, S naught. The first return map is the identity, in this case. Here's the first cohomology of the torus. Here's my class. This is 0, 1, the 0, 1 cohomology class. What's the cone? Oh, the picture, I see, the colors just aren't showing up. The cone is actually the entire upper half plane, right? Because these are cohomology classes. They're represented by curves which are not vertical. And those curves are transverse to this flow. And when you look at the first return map, it's going to be a rotation. So here's a curve. So if I think about this, I go up, and actually the first return map here is the identity. But here's another class, this class C2. The first return map is now like a rotation of order 2. So if I look at all these curves that are transverse to the flow, the first return map is some homomorphism of the circle, is some finite order 2. But so in our case, though, the first return map is a pseudo-Anosov. Why? Because the surface being transverse to the flow means it's also transverse to this two-dimensional singular foliation, right, on the 3-manifold. And so when you flow and you return to yourself, that foliation on the surface is invariant. And that gives you your stable and unstable foliations on the surface. Okay, where this function is actually the Euler characteristic, or negative Euler characteristic. So there's a linear function here. So at each level, the Euler characteristic of those fibers are growing linearly. In particular, if you take a primitive class, so something that's not a multiple of another integer class, then it turns out that the fiber has to be connected. So if you go up and you take primitive classes that are like way up here, then they have really big genus. So you get lots of pseudo-Anosovs on lots of different genus surfaces, genus going to infinity. So this is a way of generating lots and lots of pseudo-Anosovs. Okay, and each one of these has some quadratic differential associated to it. There's a really pretty picture for how to think about these quadratic differentials due to McMullen that I can point you to the reference to or tell you a bit about if you like, but I think this is a really nice. All these different quadratic differentials, they're kind of related in some way. Okay, so here's our conjecture. This is with Rafi, Rouse, Shinkle, and Verberne. So if I look at the integral classes up here, for which this is not lonely. So remember, we're looking for lonely quadratic differentials or lonely pseudo-Anosovs. So what I want to say is that most things here should be lonely. That's the conjecture. And so if you look at the ones that are not lonely, and you should projectivize. So you look at in the projectivization, we think it should be finite. So here's a sense in which generically the pseudo-Anosovs that arise here, they should be lonely. That's our conjecture. We can't prove it, but we can't even find a single example. Okay, so there's the conjecture again. Here's our theorem, though. So for any setup like this, we have our fiber 3-manifold, we have this cone. We look at the set of elements for which the Veech group contains parabolics. So if you contain parabolics, you're definitely not lonely, right? Because you have the parabolic and your pseudo-Anosov, that's going to generate, you're going to see a free group inside of there. So when you have parabolics, you're definitely not lonely. and that's at least locally finite. So it's maybe kind of a step in the direction of the conjecture. We're not saying that these are lonely, that the lonely things are local, the non-lonely things are locally finite, but at least most things don't contain parabolics. That's the upshot. Okay, so we have to assume something from number theory. This is assuming Leininger's conjecture from number theory. So Leininger's conjecture is something about Mahler measures of monic integral polynomials being bounded away from 1. Maybe I'll say a little bit about that. But so we don't have an absolute statement. Sad. Even more sad. Not only can we not prove the conjecture, we have to assume this fact from number theory. But I think people believe this anyways. All right. What are the key ingredients? There's a theorem by Verberne and Leininger which says that if you take the trace field of this Veech group, okay, so you have a Fuchsian group, you take Q, adjoin the traces of the elements in the Fuchsian group. They prove that if that trace field is not totally real, so first of all, maybe not obvious, but this is actually a number field. It's a finite extension of Q. And so you look at all embeddings into C, and it's totally real if all of them land inside of R. Okay? So what they proved is that if it's not totally real, then there's no parabolics. Or said differently, if you have parabolics, then it has to be totally real. And the other thing we use is McMullen's Teichmuller polynomial. And then various other things. So let me just show you a picture. So we did some experimentation. Here's primitive elements, and this is in the mapping torus of the simplest 3-strand braid. So basically 2 and 1 on the 4-punctured sphere. You look at the mapping torus, and it's 2-dimensional homology. These blue things, these are the places where you have totally real trace field. So these are potentially, where you might potentially have parabolics. And all the yellows are no parabolics. So all these yellow things are good candidates for lonely dudes. Okay. Maybe I'll just say very briefly an idea of the proof. So we use the Teichmuller polynomial and Descartes' rule of signs. I don't know why I just like using Descartes' rule of signs. To bound the number of Galois conjugates of the stretch factor, then we apply a theorem of Fried together with some of the stuff Thurston to say that if I have a sequence of distinct classes that are going off to infinity, but they're pre-compact in the compactification or in the projectivization. So they go off to infinity and they don't projectively converge to the boundary of the cone. Then the stretch factor actually has to go to 1. And then Leininger's conjecture tells us that there are non-real Galois conjugates. So if this is true, there are non-real Galois conjugates, call it tau n, of the stretch factor, that are not on the unit circle. Okay, if they're not on the unit circle, then when I take the element plus, when I take the number plus 1 over the number, it's a non-real complex number, and that gives me a Galois conjugate of the trace, which is... So it's not particularly hard, but it does sort of rely on some harder things. Okay, so maybe in the last few minutes,
You started late.
No, but I accidentally alerted Siri that I was going to start answering a question. I think maybe when I raise my hand, that's it. Okay, we're almost done. See, 10 out of 11. Okay, so these classes, these are like rational points in here. So this is a dense set inside of there. So there's lots of examples that you have to play with, and this should give you sort of lots of examples if the conjecture is true. But it's pretty small, right? This is essentially an open set in projective space. And so this countable dense set is pretty small. So what about everything else? So it turns out that the rest of the points also have a nice geometric description. And here now the infinite type surfaces are going to come in. So if I take any alpha, which is in the cone, but not a multiple of the integral classes. Okay, so now I'm taking an irrational class. Then there's a closed one form on this 3-manifold that is representing my class, and now I'm going to think about Durand cohomology. So this closed one form is representing the class, and it's positive on the vector field that generates the flow. So if you like, the closed one form is transverse to the flow. So that means that if I take the kernel of this closed one form, that's the tangent space of a foliation of the 3-manifold that's transverse to the flow. So let me draw a picture. Okay, probably can't see it here either. So here's my picture again on the torus. I've got this flow. And then let's take an irrational class, so that's alpha here. There's some foliation, so this is a foliation by a line with irrational slope. And the cone is right. So here's my vector field d by dy, and here's I'm going to represent my cohomology class by this one form a dx plus b dy, where these are real numbers, and I just need b to be positive. As long as b is positive, then it'll evaluate positively on this vector field. Right, it'll be transverse. Okay, so you can think about here. I've got this flow on the surface that's transverse to this foliation, and so we can just look at we can reparameterize the flow so that leaves map to leaves. If you like, you just scale the vector field by 1 over omega. Your one form you evaluate the vector field with your one form. Scale it by that, and now when you pair them together, you get 1. And so the flow is going to map leaves to leaves. And so if you're mapping leaves to leaves, and just like in the torus picture, when I'm in an irrational class, the leaves are all dense. So these are dense leaves in the 3-manifold. So these are infinite type surfaces. And I can look at the flow, this reparameterized flow that maps leaves to leaves. There's no first return time anymore because the leaves are dense. But you have a whole group of return times, right? So there's a whole subgroup, we'll call it H alpha, of return times to the leaf. So you can look at all the times when the leaf maps to itself. Okay, so let me just rewrote up here. So here's our foliation. We have this reparameterized flow that maps leaves to leaves. And what McMullen does in this construction of the Teichmuller polynomial, he actually gives you a leafwise complex structure and quadratic differential for this foliation. So now you have the foliation of the 3-manifold. The leaves are given a complex structure that varies nicely as you move around from leaf to leaf. There's also a quadratic differential that's also varying nicely. And what you see is that for every return time, every time the leaf maps to itself, and that's a dense set of times, every time the leaf maps to itself, you get an affine homeomorphism. So now we don't just have a single pseudo-Anosov, we actually have a whole abelian group of pseudo-Anosovs. So this is kind of a weird thing. You have an infinite type surface, you have a single foliation, a pair of topological foliations, in fact measured foliations, and a higher rank abelian group of pseudo-Anosov homomorphisms that are commuting. Okay, our theorem is that in this case, then in fact these are lonely. So if you look at the irrational things, they're all lonely. And that's why I wanted to call it elementary hyperbolic instead of virtually cyclic, because now in the infinite type case, this is maybe the more natural thing to think about. And this was why we suspected that maybe this is where our conjecture is kind of coming from, and we tried really hard to use this to prove that an arbitrary or a generic integral class. You think about like it's a limit of these irrational classes, and we were trying to prove. We were trying to find, lonely integral classes using this. In fact, so the image of this group inside of the Veech group has finite index. So basically, these pseudo-Anosovs that you're seeing, that's basically the entire Veech group. And let me just also point out that there's a lot of work that's been done on Veech groups of infinite type surfaces, these infinite type translation surfaces. There's a really cool paper by Chatitsky, Smitherson, and Valdez, where they show that you take any countable subgroup of PSL2, in fact PGL2, so in the infinite type case you can have non-area preserving things. It turns out that doesn't happen here. Basically any countable subgroup is the Veech group of some translation surface. So this is really something special about the 3-manifold. That what they're telling us is that you should expect to see any kind of behavior in a Veech group, and so the fact that we're getting these lonely things is maybe suggestive that this is still a good place to look. And then I also mentioned Bowman here. So Bowman constructed an example. He had the first example of a lonely pseudo-Anosov on an infinite type surface. That turned out to be finite area, and it was kind of a natural place to look also because there was a limit of finite type surfaces. Anyway, that's it. Thanks.
Any questions?
Is there anything known about the arithmeticity of the Veech group?
Yeah, so
That sort of seemed to be that proof you gave, sort of have lots of arithmetic flavour.
yeah, so it turns out that so arithmeticity of the Veech group is equivalent to the half translation surface being tiled by well, up to affine deformation, tiled by squares. So the square tiled surfaces are precisely the ones, and there's lots of equivalent formulations. If you have a pseudo-Anosov whose stretch factor is a quadratic irrational, then in fact its Veech group is a lattice and it's arithmetic. But because the Veech groups are never co-compact, they always have parabolics. Arithmeticity is really that you're commensurable with PSL2Z. That's right.
So should appear one by Leiner's condition?
No. No. Sad. More sadness. I didn't mean for this to be such a depressive talk.
Well, I have an elementary question, I guess. And so these groups have actually Taylor space, and they preserve. They add this inside Taylor space because they preserve, although they are groups so easy to add.
Yeah.
You don't think of them as acting on the upper plane.
Yeah.
They add on certain disk in certain space. So in this sense, I suppose one can ask, what's the quotient of this?
Yeah, right. So
You said that it's never compact.
it's never compact. There's always
Is it related to the Riemann set you started with in the picture, or what? Sorry.
right. So I don't know any close relationship between that Fuchsian group and the Riemann surface that you started with. I don't know if there's a nice relation there. There are various. So there are lots of constructions of these, but it turns out that as the genus grows, it's not particularly robust, and so there's lots of things you can do with branch covers. But basically, so if you want to think about like lattice examples, then maybe it's now been proved, but it was conjectured that once the genus is big enough, then the only lattice examples that you get come from branch covers of lower genus. And so maybe it sort of boils down to thinking about these kind of low genus examples, and there's a lot that's known about like what the Fuchsian group is. So in genus 2, this result of Kalta and McMullen that I mentioned, there's been a lot of work that built on that kind of computes the signature and everything for those Fuchsian groups. And then in Veech's original construction was kind of in all genus, he found these finitely many things that come from polygons, these very symmetric polygons. And those were all triangle groups. And then there are these funny examples of infinitely generated Fuchsian groups. So for example, no one knows if there's any example where the group is finitely generated and purely hyperbolic. So oftentimes people understand more about the group by finding parabolics, because parabolics correspond to these periodic foliations on the flat surface. So there's various things that are known, but yeah, it's still pretty mysterious.
Any other questions? Okay, let's thank Chris again.